Hi, it's good to see you again, dear friends. Today we're talking about exoplanets with Diana Dragomir. Welcome back, Diana.
It's good to be here. Thank you for the invitation.
Diana Dragomir is an assistant professor at the Department of Physics and Astronomy at the University of New Mexico in Albuquerque. What is
An exoplanet? It is a planet that is located around a star that is not the sun, so a planet outside the solar system which orbits or revolves around another star. We detect them using different methods. One method that I think we'll talk about more today is the transit method. It's also the simplest to explain. It's a method where if the planet's orbit is aligned with the line between us and the star, then we can observe a small decrease in the star's brightness. When the planet passes between the star and us, I rely on this dimming of the star's brightness. We can measure the size of the planet, and if we continue to observe that system, we can also measure the orbital period. So, how long does it take for the planet to make a complete orbit around the star?
and if it's not aligned with the direction, what do we do?
Then it's more complicated. But I can tell you that in that case, it's very hard to measure the size of the planet, and many times we can measure the weight of the planet. So everything gets stirred up. But even the weight is very hard to measure accurately, and many times it's more of a limit. So we can measure the minimum weight of the planet. Or we can say that it's roughly about twice the weight of Earth, but plus or minus half the weight of Earth. So it's much harder to measure the physical properties of the planet if it doesn't transit, and that's why we're going to focus a bit more on the planets that do transit, especially for today. But there are methods. It's just that in general they're a bit less precise.
And what are the different types of exoplanets and how do they compare to the planets we know from our own solar system?
That's a very good question. So, so far we've discovered planets that are similar in size and mass to Earth, as well as planets that are similar to Jupiter and Saturn. But we've also found many planets that are, in terms of size, between the size of Earth and the size of Neptune. For example, Neptune might seem small to some people and large to others. It's a gas planet, but actually it's about 4 times the size of Earth. Many planets have been discovered around other stars that are 2 or 3 times the size of Earth, something that doesn't exist in the solar system. And that's one of the sub-trends of the last decade, so to speak, or even more than that. But these planets are the most common around other stars. So these planets that don't exist in the solar system are among the most common in other systems.
And so, being between Earth and Neptune, are they rocky or gaseous?
It depends. Sometimes they are rocky, other times they are gaseous. So that was the big question when we started to discover these planets. What are they like? Are they more like Earth or Neptune? Moreover, it seems that it depends a lot, but not only on size. So there are some planets that are, let's say, twice the size of Earth and seem to be rocky, and others also about twice the size of Earth, but have a thick atmosphere, which could make them like a mini gas planet. So the variety is amazing.
Can you explain the significance of the habitable zone in exoplanet studies?
So the habitable zone is defined as the area where we think liquid water can exist. So it mainly depends on temperature. So at a certain distance from the star, the temperature drops enough for water to no longer be in a gaseous state, but to be in a liquid state. And that's roughly where the habitable zone begins, and further out. When the temperature drops too low, water exists only as ice. So basically, this area between the two boundaries is the habitable zone. It's calculated a bit more complicated than just temperature, how the temperature drops with distance from the star, but generally, that's how it's defined.
And from this perspective, what are they and how do they contribute to the research of these exoplanets? Missions like the James Webb Space Telescope or Transiting Exoplanet Survey Satellite, the Transiting Exoplanet Survey Satellite. Yes,
Transiting Exoplanet Survey Satellite discovers the planets, and the James Webb Space Telescope discovers or studies their atmospheres. Out of all the planets, out of the selection, Transiting Exoplanet Survey Satellite discovers hundreds or even thousands of planets. With James Webb, we can choose the most promising ones, the ones most likely to have an atmosphere, or the simplest to study. And we observed their atmosphere with Genuso, which is much larger and can study these planets in more detail.
In your research activity, you have studied super-Earths and sub-Neptunes. How do these planets differ from those in our solar system, and what have you found out about their composition?
Yes, so super-Earths and sub-Neptunes are these planets that are sized between Earth and Neptune. Well, as we discussed earlier, it's complicated. In general, the ones that are above, let's say 1.6 or 1.5 times the size of Earth, tend to be mini planets, mini gas giants. The ones that are smaller than 1.5 times the size of Earth. They are planets that are rocky, generally, but it also depends a lot on where the planet is located. So, if a planet is very close to the star and receives a lot of radiation from the star, a lot of infrared, more in the range of life, then it can even be a bit bigger and still lack an atmosphere. So we've discovered a few planets like this that are like that. That's because it is. The radiation from the star tends to strip away, to eliminate the planet's atmosphere quite quickly, and then the planet is left with basically just its core. Rocky, and we need...
in order to look for life, we need a rocky planet with a bit of atmosphere.
That's what we say, because here we know life on a planet that matches this description very well. Only recently, I think some astronomers have started to get impatient with these kinds of criteria and have begun to consider that maybe they've discovered life on other planets as well. I think we'll talk a bit more about that later.
In your research, you look for planets that are more like Neptune. Haven't you gotten impatient? What makes you stay in this field?
I'm also interested in the question of life, so whether there is life beyond Earth, but also simply how planets form, and including how common is the solar system or systems that resemble the solar system. The solar system. And I think that by answering these questions, we will also indirectly get a clearer answer about whether or not life exists. I know about planets, I don't know about other stars. I think yes, but that's simply an opinion, and an opinion based on statistics and the number of planets we know exist. Until today, we've discovered a few thousand planets, but we can start from that number and knowing how many stars we've looked at. We can say that each star has approximately a gaseous or rocky planet. And we're starting to get a bit of an idea about how common rocky planets are in the habitable zone. And for now, we don't know this number very precisely, but it seems it's not zero, even if it's just 1%. Since there are trillions, or at least millions, at least billions of stars in our galaxy. For me, that's enough of an answer to the question, is there life? To the question.
In your research, you mentioned the hot Neptune desert. Can you explain what that is and why it's important?
Yes, so the hot Neptune desert it's not in the habitable zone. Let's start with that. So it's an area. It's a desert in terms of distance. So, okay, it's a desert because it's in two dimensions. One dimension is the size of the planet, the other dimension is the distance from the planet. It's about an area very close to the star where we don't think there should be planets of that size. Between what? Planets at that distance, very close to the star, must be either rocky or very massive. And basically gas planets. So we don't think there are planets in that area because since the temperatures are very high, around 2000 Celsius many times, thousands of degrees Celsius. A planet that doesn't have enough mass to hold mass. I'm also thinking about gravity to hold a gaseous atmosphere. It should lose it completely. That means either you have the mass of Jupiter and then you can keep that atmosphere even against the radiation from the star, or if you have a smaller mass than that, you lose the atmosphere completely and become a rocky planet. I think I would also lose my atmosphere. Not only I, but other astronomers as well have found planets in this desert, and they are extremely interesting because, in principle, they shouldn't be there. They shouldn't exist. So what do? When we discover them, we put them on the James Webb Space Telescope and see what happens with that atmosphere and what's in it.
I read that your team recently detected an atmosphere on a rocky exoplanet. 55 Cancri A. What does this discovery tell us? Specifically?
Yes, so this is a super Earth-like planet that receives a temperature of about 2000 degrees Celsius. I didn't really believe it. Initially, it wasn't discovered. It wasn't believed that this planet had an atmosphere. But over time, with more observations, not only from James Webb, but also from the Spitzer telescope, about almost 10 years ago, we realized that there was something there. There were signs that there might be an atmosphere. And with James Webb, we discovered it on the surface of planet A. Carbon monoxide, actually, we don't know if it's carbon monoxide or carbon dioxide because we don't have the precision to distinguish between the two, but we know that one or both are present, and they are present in abundance, so much that it's not just a little bit. At the surface of the planet, it's clear that there is still quite a thick atmosphere, even thicker than Venus, because anyway, Venus, well, this planet, 55 Cancri E, is about twice as massive or more than Venus. And this tells us that there is still an atmosphere there where this atmosphere comes from, because it should exist. If there were an initial atmosphere from the formation of the planet, we believe it is an atmosphere created from inside the planet. At 2000 Celsius, the gases that are trapped inside the planet come out through the lava, through the surface of the planet, which is practically melted. And then these gases constantly replace the atmosphere, which is probably stripped away by the star's radiation, but it is constantly replaced from inside the planet precisely because of the heat. And that's the current theory, but we continue to try to get data from James Webb with other instruments so we can try to verify this hypothesis.
Let me get back to the test now. How do single transit events from the test data contribute to the discovery of exoplanets with long orbital periods?
They contribute well, eh? So yes, to exist small. In short, the test observes over a period of about 2 years. It observes almost the entire sky, so it looks for planets around any star that's bright enough for the test to be able to observe it. But in order to observe the whole sky in 2 years, that means that each section of the sky is observed for about a month, or at least that's how it was initially when it was launched, for almost 8 years. So each part of the sky is observed for only a month. That means that if we have a planet with a period, let's say, of 60 days, so it orbits around the star in 60 days, if we're lucky, we can detect a single transit in that month or no transit at all. If we detect only one transit, then we have a chance. Let's pick this one. So we don't know that the period is 60 days, but if we detect only one transit, it allows us to say that at least the period is longer than about a month. And in this way, we have discovered planets with periods of up to hundreds of days. And I have a student who is currently working on a system that has a planet, or it could be a magic plate.
Rangoduna.
We don't know for sure, so the weight is somewhere between a planet and a mini star, so to speak. But it's still a very interesting object, and it only transits once in all the transiting exoplanet survey satellite observations. And it seems to have a period of 3,000 days, which is a record 10 times greater than the previous record. And we're getting ready to finish this article and submit it to the Nature Journal to see if it gets accepted. But it's a very interesting system because not only is there this object that transits, but there's also a super Earth and a gas planet with an intermediate mass between the two. And we don't really understand exactly how this system exists because it seems there are many dynamic interactions between the three planets. And we're trying to understand if it's stable right now or if it shouldn't be. If not,
You have to write to Newton, because you know Newton, that's how the system is stable.
it's stable, but it seems to be constantly changing. Okay. Initially, a colleague from Massachusetts Institute of Technology said, I have a problem. It seems the system isn't stable. Okay. Yes, that's really a problem. But in the meantime, she said, no. I didn't read the simulation results correctly. And then she realized that, in fact, it changes the ellipticity of the orbit over the course of several million years. And it seems that this will continue for some time.
Because you mentioned that you're about to publish an article, I would like to ask you if you can tell us what are some of the most interesting developments or discoveries in your field that you expect to see published by you, your collaborators, or others in the near future?
Among the discoveries that James Webb has made so far, there are a lot of surprises in terms of results, including a molecule called sulfur oxide, 2-sulfur dioxide. And for me, another very interesting thing is that objects with the mass of a planet have been discovered, so several times the mass of Jupiter, but alone. So they formed like a star without their own planets, and they didn't form around a star. And yet they have a very low mass, and that causes some problems in terms of planet formation, because we thought that a planet forms in a disk of dust and gas around a star. If now the same mass of a planet can forming like a star rather from a contracting cloud of gas, it really changes a lot of our ideas about how stars form compared to planets and whether there really is a difference or if it's more like a continuum. And sometimes it can be a very massive object that forms like a planet, while at the same time there might be a less massive object that forms like a star. So we're starting to blur the lines a bit between stars and planets and how each of them forms. Those are just two. There are a lot of other unknowns, so it's really hard to predict what will happen. But I can say this after thinking about it a bit, a very important project. Currently, 500 hours of time on James Webb are dedicated to TSA. Is to find out if the planets around red stars, which are smaller than the sun, but also have irradiation, are linked to much stronger traces. And because of that, many astronomers believe that the planets around these stars have lost their atmosphere. even if they are at a lower temperature than many others from the start of the system. But we're not certain. So, one project is to observe a few dozen so-called rocky planets. We're not sure, but small ones, so they have a good chance of being rocky, and see if they still have even a very thin atmosphere. Like Earth, so Earth is a rocky planet, even though it has an atmosphere, because the atmosphere is very thin, to see a bit whether, in general, planets around these stars have an atmosphere or not. And in the next few years, I think so. And we have a clearer answer, and that helps us decide if it's worth it to continue searching for signs of life on these planets, which are easier to detect. And that's why many astronomers consider them interesting for life. Or if not, is it worth it? And we need to go back to the stars that are similar to the sun and look for life on planets around those stars. Don't forget to give thanks, which in some ways are even more like the solar system.
Sometimes you dream about these planets when you go to sleep, wondering what it would be like, what they look like, since you know so much about them that you can imagine them.
I don't dream at night, but I often think about it when some discoveries appear, which, let's say, sometimes can be exaggerated, or even if they're not exaggerated. We always try to interpret the results a bit more than we think is clear. And that's normal, but many times I wonder if we managed to reach that planet or not. And we realize that it's completely different from all the hypotheses we had, and that keeps me a bit objective. And in this way, I mean, to keep not looking for something in the world and to remind myself that science is about science, about research. Yes, we find answers to questions, but often they are probabilistic, so there is only a probability that the answer will be the same, this answer. But often new questions arise, and we have to keep gathering data to answer those questions as well. That doesn't mean we're not progressing. It's just that I have to, yes, remind myself to stay open and not to look for something specific. When I try to ask you a question,
The last question, probably everyone asks you about extraterrestrial life and about intelligent extraterrestrial life. I'd like a more specific answer if possible. About how many planets in our galaxy could have one thing or another, roughly where, something more than just saying they exist somewhere but we don't know where.
I can't give an answer, that's it. We don't know where. I can give nuances, again. Yes, so besides, well, I think there is, or there was so-called intelligent life. What does intelligence mean for life, which doesn't look anything like us, right? And that's a philosophical question, but besides that, I have something a bit more concrete. What is the time span? If we think about how long humans have existed on Earth, not to mention how much longer we'll exist. Let's say we'll be around for a few more thousand years. It's possible, but we don't know for sure. It's such a short span in the life of the universe that I think it's harder to even... What's more complicated is the chances that we exist at the same time as another short period of intelligent life on another planet. Those chances are very low, so how much more likely is it that intelligent life has existed before we have the ability to find it or after we no longer exist? But the chances are very small that it would be in exactly the same period of time as us. And that's simply an argument based on the fact that humans appeared on Earth very late.
In the life of the system, and that they can disappear very quickly.
And that they can disappear. But even if we don't consider that, it's still a very short piece of the system's life. Or us. And I think that's what makes me say that I don't know. I don't think we'll be able to find the signs. Intelligent life is more based on that. But that doesn't mean they didn't exist, or that they won't exist, or that they don't exist now. But they are very far from us and we can't detect them.
Tell us what you're working on now and what keeps you up at night, what gets you up in the morning.
Right now I'm in Santa Barbara at a physics center where there's a program like this. where several researchers come together to discuss specific problems. In this case, it's about rocky planets, but the ones that are very close to the star, how they formed and how they got so close to the star is not exactly clear. My field is more theoretical than my work, but it's helpful to know about other fields too. So I learn a lot here. But I'm in California this spring, mainly because I'm working with a collaborator at the University of California, Riverside, on a question that has been bothering me for a few years, or let's say for at least 2-3 years now. What is the connection between Jupiter in the solar system and the rocky planets inside Jupiter? I think that question also relates a lot to presence. There are a lot of possibilities, a lot of questions and answers that are starting to come up, but especially one of the ideas is that if Jupiter didn't exist, the planets inside the solar system could have been much more massive and larger, and then they could have even become mini gas planets. In that case, it's not clear if we could have life or if we could even exist now. We're talking about planets without a surface in front, maybe some kind of internal ocean, but more likely something like planet K2-18b. And that's because the material in the disk where planets form is held back. It's blocked by the presence of Jupiter, which we believe formed first, right? And then this material remains mostly outside Jupiter's orbit and prevents the inner planets from growing. So then they stay small, actually. They stay the perfect size for life.
Thank you to the whole universe and thank you to Diana for being here.
Thank you.